Okay, I've selected two questions here which I think are quite challenging. So I recommend you pause the video and get a pen and paper and a calculator and spend maybe 15 or 20 minutes working through these two questions. I would say these are grade A standard, possibly getting towards A star in places, but they're certainly quite challenging questions. So see how you get on. This first question, part A, is a standard question. That's probably only going to be 2 marks in the exam. And as always, select the formula. So look in the formula booklet if you don't know it. Resistance is equal to rho L over A. And we don't really need to do much there. We just need to substitute because we know the resistivity and we're given the length and the area. And in this case, we don't even have to calculate the area, so it's relatively straightforward. So we can find the resistance as 0.023. So that should be a straightforward 2 marks. Part B, it says if we double the length of the wire, but we keep the cross-sectional area the same, how does the resistance change? Well, that should be relatively straightforward to answer. Explain your reasoning. Now, what a lot of students in the exam would do is just say, well, if we've doubled the length, it's going to be double the resistance, and you don't have to calculate it, but for good measure, you might want to do that. Explain your reasoning. That's that extra level of detail. You've got to include that. Otherwise, you'll only get 1 mark. So we need to say either resistance is proportional to length. Even better, and this is a good exam tip, make reference to the formula. So according to resistance equals rho L over A, the resistance is proportional to the length. So that's the extra level of detail which will get us the 2 marks. Right, in engineering applications, why might copper be preferred over materials with higher resistivity despite its cost? Right, so this is the kind of the application of science, science in society, explaining a rationale. And for 3 marks, this is quite difficult. So I would say this is an A, possibly an A star question. So we need to answer it in the context of the question. So if the question is about resistivity, and it mentions resistivity in part C, we have to make reference to resistivity. So they've told us the resistivity of copper. We need to say that that's a relatively low value. So this is drawing on our knowledge of how does this compare to other materials. So it's a low resistivity. So if you make a copper wire, it will have a low resistance. So resistivity and resistance, we can mention both of those. And then this is a bit of a synoptic question, really, because we need to make reference to the power formula. So if we have a low resistance, we could say, well, P is equal to I squared R. So if the current is a particular value, the lower the resistance, the lower the power across that component. So a good word is power dissipation or heat dissipation. So if we could reduce the resistance of a component, we will reduce the heat loss and therefore the power loss in transmission. So that would give us a 2nd mark. But why is that useful in engineering applications? So could we think of an application? We could talk about power transmission. So even though it hasn't mentioned that in the question, we could talk about over a long distance, even though copper is relatively expensive as a material, the amount of energy we are saving, therefore money, is going to work out beneficial. So that's quite a difficult question. So most students answering this might just get 1 or 2 marks. So we need to get sufficient detail in the written response. Let's have a look at question 2. So part A says find the resistance. So clearly there's a bit of repetition here in terms of the style of question. A resistivity question will almost always ask us to find the resistance or the resistivity. So this should be relatively straightforward. But if you look at the marks, it's 3 marks because we have to be careful with units. So similar to question 1, R is equal to rho L over A. We've got the resistivity, that's fine. Watch out for centimetres. So 5 centimetres divide by 100 to get 0.05. Watch out for millimetres squared. So a very common mistake here would be to divide by 1,000, but this is in 2 dimensions. So we need to divide by 1,000 squared, which is 1,000,000 or 10 to the minus 6. And you should have noticed, because if you didn't divide by that extra 1,000, then your resistance was probably going to be very, very large. And that should have made you think maybe I've made a mistake here. Okay, part B, again, so a little bit more tricky here. So we're changing the length. It hasn't told us the new length or the new area, so we're going to have to work those out. Now, you should be able to work this out with your knowledge of maths. If we increase the length by 2%, so that's 1.02 multiplied by the total length, we can work that out as 0.051. If we've decreased the area by 1%, we want to find 99% or 0.99 of the area, 0.01 10 to the minus 6. So we get our two new values here. So that's possibly a little bit tricky. Once we've done that, we're just once again substituting the new values and we should get a slightly larger resistance. So you should be thinking at this stage, does that make sense? I've increased the length. Yes, that will increase the resistance. And I've decreased the area. That will also increase the resistance. So even though these changes are really quite small, they are detectable. And this leads us into part C. I think the previous question said a strain gauge. I don't know what a strain gauge is. So strain gauge is what it should have been. So explain the basic principle of strain gauge. Now, this is what some exam questions do, and this is where the A-star marks are. Strain gauges are not on the A-level specification, as far as I'm aware. But you need to apply your understanding of physics and what we've done so far to think, well, how might this be useful? So strain gauges are little devices which you can attach to components, and these are used in engineering and construction to either monitor or test changes in the length, so very, very small changes. And a strain gauge is basically a long piece of wire, which is not necessarily coiled, but kind of wrapped backwards and forwards, so you can get a long piece of wire there. And when the component is stretched, then that will have a change on the length of the wire, and also it will change the cross-sectional area. So this leads us into our answer here. So stretching a strain gauge increases the length and decreases the cross-sectional area. So we're almost repeating what's been said here, but that might get us a mark. This changes the resistance once again according to. It's always useful, rather than just say, well, the resistance will be different, we need to say, well, why is that? According to which formula? So according to our formula, R is equal to rho L over A, I've increased L, I've decreased A. Both of these factors will combine together to change the resistance, to increase the resistance. And then we could make reference to these answers here. We could say, well, this is 7.5 and this is 7.7. It's not a massive difference, but it is detectable. So the new resistance or the change in resistance can be measured or detected, and then with that information, the new length can be calculated, or some information can be implied or inferred with that information. So, okay, good. So this is examples of difficult questions on resistivity. So certainly grade A, possibly getting towards an A star with the part C sections.